Hello, class. So on this video, we're going to continue on section 6.1. Right? In the previous video, we introduced this notion of a function being of exponential order. What did it mean to be of exponential order? In practice, what it meant is that your function grew at most as fast as a constant times an exponential. Right? That's what it meant in practice, right? Just was telling you something about the growth rate of the function. In practice, we have this inequality, right? So in order to verify that a function is of exponential order, we have to find constants k, a, and m that satisfy this inequality, right? So we did examples of that, right? In some examples, I just gave you, okay, these are the inequalities, right? And you can identify what m, k, and a are in each case. However, in the last example, I showed you how do you actually derive this inequality. And I show you that the way to do it is basically the same way you would treat a trig identity. You start with the left-hand side, and then you write down a series of inequalities until you get to something that looks or has the right form. So here, for example, we started with the absolute value of 2 cosine of t. Right? We use the properties here, right? So here on the right-hand side, so the fact that you can take the absolute value of each factor whenever you have a product. Right? Then we use the fact that the absolute value of cosine is less than or equal to 1. Right? And finally, the fact that 1 is always less than or equal to e to the t. Right? So that's how we got all of these inequalities. And we got, in the end, something that has the right form. A constant times an exponential. Right? So we read everything off. Right? We saw that m equals 0, k equals 2, and a equals 1. And that was the idea, right? That's how you would show that something is of exponential order. Now, we can finally talk about how exponential order relates to a function being having a Laplace transform. And it's basically almost it. There's only one more thing you have to check, right? So suppose that a function f is piecewise continuous on 0 to infinity, and that f is of exponential order. That's all you need. And I'll explain what piecewise continuous means in a moment. But as long as those two things are satisfied, then the Laplace transform of f exists for all s greater than a. Now, notice that this isn't only telling you that the Laplace transform exists, it's only also giving you the domain of the function. Now, what is this a? Well, this is the a that comes from the inequality of exponential order. Right, so again, in practice, we won't be doing much with the domain of the Laplace transform. Not of the function itself, but given a function, take its Laplace transform, you have a function of s. So talking about the domain of that won't be too important because mostly we're going to be working with the Laplace transform as just expressions, algebraic expressions. You're just going to try to solve for s. That's going to be the idea. That's how we're going to be using them. However, you can see that theoretically it is important, right? And it shows up here. Now, what does it mean for a function to be piecewise continuous? Well, the first thing that's important to know before I show you what it is that continuous implies piecewise continuous. Right? So whenever you have your function f being continuous, you don't have to worry about anything. Right? So what's piecewise continuous? A function, let me do it here. A function is piecewise continuous. Let me give you an example. If it's a piecewise function that is continuous on each subinterval. Remember that a piecewise function is a function which is defined potentially differently on each part of its domain. So let me give you an example. Suppose I divide my interval into a couple subintervals here. And I'm going to draw a function here. I'm going to draw a function that looks like this. Start something like this. Here it might look something like this. Here maybe something like this. And then maybe here it looks something like this. Okay. Now, this is an example of a function that is piecewise continuous. Right? You can see that it's not continuous, right? Because you cannot draw this graph without lifting up your pencil. However, on each subinterval, right, so on each open subinterval, so let me write those here with a different color. See, let's use, so we use red. Okay, let's use red. On each open subinterval, the function is continuous. Oh, and this one goes to infinity, the last one. Right? So let me do ... at the end to show that it goes to infinity. Right? So it's an example of a function that's piecewise continuous because even though it's not continuous as a whole, in each subinterval, it is continuous, and you can verify, right? Look at each subinterval. You can draw the graph in each subinterval without lifting up your pencil, right? So that's what it means to be piecewise continuous, right? In a lot of examples, we're going to be working only with continuous functions, but soon, and very soon, in the next video or the next two videos, you're going to see already an example of a function that is piecewise continuous, but we can still find its Laplace transform. And in fact, piecewise continuity is going to be very important for us when we start talking about step functions. They're going to allow us to do a lot of really interesting things with Laplace transforms. So it is important to know what piecewise continuity is. But other than that, that's all. Again, continuous implies piecewise continuous. And in terms of whether a function has a Laplace transform, as long as your function is piecewise continuous and it's of exponential order, you are guaranteed that the Laplace transform exists. So in the next video, we're going to see examples of how to use this theorem to show that the Laplace transform of a function exists without actually having to find the Laplace transform. And that's the last thing I want to say. If I ask you, and that's the note that I wrote here, if I ask you to show that the Laplace transform of a function exists without actually computing it, then you have to use this theorem. This is the only other technique that we have. We either compute the Laplace transform, and we know that it exists, or use theorem 1, where I gave you the lists, or I ask you, compute or verify that the Laplace transform exists without actually computing it, in which case you would have to do what this theorem says. You would have to show that your function is piecewise continuous and show that it is of exponential order. Right? But again, we'll see how to do that in the next video.